Section 3.9, Related Rates. The idea with this section is to express the rate of change of one quantity in terms of the rate of change in another quantity. Let's start with an example. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? What we are given is a rate of change of volume with respect to time, and we want to use that to find out the rate of change of the radius with respect to time. We also want to find that rate of change at a particular moment, when the diameter is 50 centimeters, which also means that the radius is half of that, 25 centimeters. What we're going to need to start with is the fact that the volume of a sphere is given by the formula V for volume equals 4/3 pi r cubed. And also we're going to need that the rate of change of volume with respect to time can be interpreted as a derivative. dV dt equals 100 cubic centimeters per second. So we'll start with the formula. V equals 4/3 pi r cubed. And what we are going to do is take the derivative with respect to the independent variable, in this case time. And we're going to do that on both sides. And what we're going to see is this is just another application of implicit differentiation and the chain rule. So on the left-hand side, the derivative with respect to t of v is quite simply just dv dt. That is what that means. On the right-hand side, the 4/3 and the pi, those are constants. So we can factor those out. And now we just need to take the derivative of r cubed with respect to t. This just uses the chain rule where the 3 drops down as a multiplier, the power reduces by 1, and then we have to still take the derivative of the inside function, in this case r, with respect to the independent variable t. So here's the first part of the chain rule, 3r squared, but then I have to multiply by the derivative with respect to t of r. And what I just wrote, the derivative with respect to t of r, that is just dr dt, which is the rate of change of the radius with respect to time, which is what we want to find, rate of change of radius with respect to time. So, let's simplify what we have. dV dt equals 4/3 pi times 3r squared. That's just going to turn into 4 pi r squared, because the 3's would cancel out, and then times dr dt. And since we just want to solve for dr dt, this means I can take dV dt, the derivative of the volume with respect to time, and just divide it by 4 pi r squared. So now to get a numerical answer, which is what we want, we can now use the fact that dV dt is 100 cubic centimeters per second, and we can also remember that we wanted to do this when the radius was 25 centimeters. So I'm just going to plug in 25 for radius and 100 for dV dt. So 100 cubic centimeters per second divided by 4 times pi times 25 centimeters squared. And if you think of how the units are going to cancel, I'd have cubic centimeters divided by square centimeters. That just leaves me with centimeters, and then I still have per second. which again makes sense because dr dt should be the rate of change of radius, which is measured in centimeters per second. So then what I'm going to get from this is just going to end up being 1 divided by 25 pi centimeters per second, which of course we could write as a decimal if we wanted to, but this is also a simple enough form. So that's it. This whole lesson is really just an application of implicit differentiation and chain rule. And the idea is start with a relationship between two variables, or in some cases we might see three variables, then take the derivative of that formula with respect to an independent variable, and then plug in what you know, any rates of change and any given values that you have. So let's look at another one. The length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So first of all, we need some variables. Let W stand for width, and L stand for length, and A stand for area. Then the formula that we can start with is A equal to L times W. We're also given two rates. The first rate that we were given is that the length is increasing at a rate of 8 centimeters per second, which means dl dt, the derivative of length with respect to time, is 8 centimeters per second. Notice how the units act in the same way as the fraction. I have centimeters for length in the numerator and seconds for time in the denominator. And then we were also told that the width is increasing at a rate of 3 centimeters per second, which means dw dt is 3 centimeters per second. What we are asked to find is dA dt, the derivative of the area with respect to t, which means the rate of change of the area with respect to time. How fast is the area of the rectangle increasing? And we need to find that when the length is 20 and when the width is 10, and those are of course in centimeters. We'll use the product rule and implicit differentiation. So I have to take the derivative of both sides with respect to an independent variable, which in this case again is time. Notice that on the right hand side, since I have L times W, I'm going to have to use the product rule. So this means dA dt, the thing we're trying to find, is dL dt, and if we want there's a script L, the derivative of the first function and then times the second function, which is W. And then the product rule says I also need to add now the derivative of the second function, so dW dt, and then we multiply that by the first function. So that's the product rule, and the implicit differentiation is the fact that we are differentiating each of these variables with respect to a fourth independent variable. And so now I can take everything that we were given. We know what dL dt is, what dW dt is, and we know that we're looking at a specific moment when the length is 20 and the width is 10. So I'm going to plug all of those in. So dA dt is equal to dL dt, which is 8 centimeters per second. And then I multiply that by the width, which is 10 centimeters. And then I add dW dt, which is 3 centimeters per second. And I multiply that by the length, which is 20 centimeters. And you can see that what you're going to get are numbers that are measured in square centimeters per second. Since I have a centimeter times a centimeter, that's square centimeters. So this is 80 centimeters squared per second plus 60 centimeters squared per second, which gives me 140 centimeters squared per second. Notice the units for this area is measured in square units, so that's centimeters squared, and then per second because time is measured in seconds. So again, the units should always match up with what the unit should be for your derivative. So the only difficult thing that can happen from these examples is if you don't have enough information and you have too many variables. So then what you have to figure out is a way to reduce the number of variables in your formula to then move forward. So we're going to see that in this next example. A water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. So here is a great example of where you would definitely want to start with a picture. So an inverted cone looks like this. The circle is on top and the point of the cone is on the bottom. So there's our picture, and we were given a couple of things. The base radius is 2 meters, which means the circle at the top has a radius of 2 meters. And then we were also given that the height was 4 meters, which means from the top of the cone to the bottom, that's 4 meters. We're also going to need a formula that gives us some variables, and then we're going to need a way to reduce the number of variables, as we're going to see in just a minute. So down below my picture, we are given a rate of change of volume, dV dt, which equals 2 cubic meters per minute. So we're going to have to start with some formula that involves volume. So in our case, the volume of a cone is 1/3 pi r squared h, where r is the radius of the base, and then h is the height of the cone. What we are asked to find is the rate of change in the water level, which would be dH dt. Now, if the water level is changing, you can think that it's rising up. That means that the radius is also changing. So if there's a rate of change for height and volume, there's also a rate of change for the radius. But we aren't given a rate of change in the radius. So if I was to use implicit differentiation on this formula that I have right now, I would end up with a dV dt, and then eventually a dr dt and a dH dt. But I don't have anything for radius. I don't have any rate of change. So I wouldn't be able to use that method. So what we're going to have to do is simplify our formula so that we only have V and H. The way that we're going to do that is using similar triangles. So with a cone, there's an implied right triangle that you can see. If I just drop down from the center of the circle to the point of the cone, you can see that I've got a right triangle there. And that right triangle has base 2 meters and height 4 meters. If I have any smaller cone inside of that, then I would get a smaller right triangle. And that smaller right triangle would have radius r and then height h at any point, like if we were just filling it up with water. That gives us a proportional relationship, which means the 2 for the radius of the big triangle divided by the 4 for the height of the big triangle is equal to r for the radius of any other smaller triangle divided by h, the height of any smaller triangle. Which means that 1/2 times h is equal to r. Or you can say r is equal to 0.5 h. So that means our volume formula can be simplified. I can say V is equal to 1/3 pi, and instead of r, I'm just going to replace it with 0.5 h, quantity squared, times h, which gives us that volume is 1/3 pi times 0.25 h cubed, which is what I have down here. Now I can use implicit differentiation. So I'll do that below these paragraphs. So I'll start with the formula and taking the derivative with respect to time of both sides. Notice that all I have are constants and then h cubed. So this means that I would have dv dt equal to, and simplifying the arrangement of these constants, 0.25 pi divided by 3, and then times the derivative with respect to t of h cubed, which means I can use the power rule. So dv dt is equal to 0.25 pi times 3h squared, and then times dh dt. And now if I'm looking for dh dt, let's just plug in everything that we know. We know that the derivative of the volume with respect to t was given earlier as 2 meters cubed per minute. And then we also wanted to find dh dt when the water is 3 meters deep. So when h is equal to 3. So we'll plug in dv dt equal to 2 cubic meters per minute, and h equal to 3. So that gives me 2 cubic meters per minute on the left equal to, I can simplify those 3's, 0.25 pi, and then times h, 3 meters squared, times dh dt. And the units, again, are going to cancel out in a way where we're just going to get meters per minute, which is how dh dt would be measured. And you can see why that would be. The meters cubed on the left are going to be divided out by meters squared on the right, which would just leave you a meters. And then that would be per minute. So this turns into 2 divided by 0.25 pi, and then I'm also dividing by 3 squared, which is 9, and this would be meters per minute. And for this one, how about we get a decimal? So 2 divided by 0.25 pi times 9. And that gives me approximately 0.283 meters per minute, approximately as dh dt.